This could be a really fun discussion. We didn't have many opportunities to speculate. And since it's only a discussion, we can say anything we want. It's actually essential that we do. I think it's a matter of survival. Not survival of mathematics, that's independent of us, but survival of a certain traditions and certain ways of doing or practicing our field. The first issue here is, we are supposed to discuss mathematics in the real world. It can take forever, since mathematics is the real world on some level, at least for some of us. And, the discussion is endless. But there are really several aspects that maybe it would be good that we address. Some of them are intellectual, and some of them are political. They're both important. We had a tendency as a community to sort of be quite reticent in having a big view of the world like the astronomers or others. And maybe it's a good idea that we try, at least, to go in that direction. But for that, we have to put our house in order and understand what really are the challenges. I think this meeting that we are at has as one of its missions to basically define, in some ways, the areas at which we are weak rather than strong. And the weaknesses are much more interesting. I mean, what we don't know how to do is infinitely more interesting and challenging. Unfortunately, we like to talk about what we just did. And, well, that's fine, but not very productive. I sort of distributed a blurb around. There was not particular intention in it in terms of a topics that we need to concentrate on or anything. It was just an indication. This was a blurb which was given to the Mathematical Science Community Advisory Board, Mathematical Physical Science Advisory Board. So those are chemists, physicists, astronomers, and others. And the intent was to basically describe to those people on some very rudimentary level to what extent they don't have the mathematics they need. And it actually had a tremendous impact. I mean, I was surprised by how receptive those people were. On the other hand, my colleagues were not interested at all, I would say, most of the time. And there were exceptions. But there the point was made that, in effect, and we all know that in some level, but whether we want to participate in it is another question. The point was that, in effect, the state of science, or most of the sciences and technology around us, is reaching a certain level of paralysis, in the sense that complex phenomena are dealt with very ad hoc methods, which are invented on the spot. Nobody is putting the intellectual effort necessary to build the mathematical infrastructure or the language and the definitions of the geometries, the definitions of the interactions between objects that are needed in order to actually go ahead with the science. And this goes all the way from Newtonian mechanics to biology. Okay, now we would think that Newtonian mechanics, I mean, some of us think that you want the theory of all, and that would solve a lot of problems. It's true, it will, on some intellectual level. On the other hand, simple problems that were understood by Newton are still not understood by us. And the reason it's not understood is that we just don't have the mathematical tools to describe them and to deal with them. So in this blurb, there is a specific example given having to do with computation of gravitational interactions. It's a trivial thing, but it puts the point at the level showing that although we understand the laws of physics, we don't understand how it works, or at least we can't describe how it works. So I think rather than be abstract, I would maybe just try and give an impressionistic summary of this half page that you got and use it as a scaffold on which maybe we can build a discussion. By the way, again, my intention is just to have something concrete in mind. It's not that this is a particular topic we need to work on. I mean, the issue is on what level, you know, mathematics in the real world, mathematics has always been the language of the description of physical law or biological law or any law in which there are specific rules of operation, and mathematics was used both as a language to formulate problems or to define structures and as a language to describe relations and interactions between objects. And the real issue is, and it has always been like this until this century on some level, that we sort of focus much more on our internal needs at some times of this century, not all along. And sort of disconnected. There are two issues. One is, we could all become applied mathematicians, but that's not the point. The point is that the wealth of mathematics actually was nourished essentially by this outside interaction. And I think the real question is, what's in it for us as pure mathematicians? What kind of insight are we going to get into our own internal core mathematics by actually viewing external problems, okay, or problems that we think are external, although they're just manifestations of things that we have seen all our life. Tomorrow I'll try and give some example in complex function theory or something, which are very simple, which when viewed from the point of view of music suddenly make sense, but viewed as a formula in complex analysis are just a complicated formula. So let me be for a minute a little bit more precise. I just want to summarize briefly what was in this blurb that I gave you. The issue is the most elementary problem of all. You have a tremendous number of gravitational masses in the universe, and you just want to compute where they're going to be maybe a year later or maybe a month later and so on. So those masses are distributed. Well, we have Newton's law at our disposal. It's not a big deal. We know that we have, say, n masses. There are n squared interactions. And we can just compute it. Okay? When you do that this way, which is the way people have been doing it, nothing works because you have too many masses. And computation is intractable. And you would think that, and you really haven't gained any insight into the problem. There's no insight whatsoever. I mean, all you have is all those little masses interacting. On the other hand, there are a lot of structures out there. There are galaxies, and there are other groups and clusters of stars and other masses around. And you want to understand how the various objects interact with each other and work together. Again, naively, there's nothing, right? Just put it in a computer and let the computer do it, and everybody is satisfied and happy with this. In effect, it's very easy. It's clear that this is a completely dumb and impossible way to compute. By the way, when I say impossible, and I know there are some people who don't look normally at numbers, you know, when you have 1 million points or 10 million points and you square it, it becomes a pretty big number. And very quickly, if you have to do this every tenth of a second and you have to do it for a year, it's a very, very big number. And it's just intractable. On the other hand, if you could do the computation in order, say, corresponding to the number of points that you have there, well, you have a chance. Coming back, before I describe it slightly more, let me just say, I view the issue of being able to compute it effectively as a problem a la Gromov. It's a good way to ask questions about structures of things. If you can do it, you have understood exactly how things are organized and interactive. You understood geometry and so on. If you are incapable of doing it, but just do it naively, well, that's fine. You understood it on some Newtonian level, but that's it. So there, coming to this gravitational masses thing, There's only one observation that was made by Newton, is that if you want the impact of the moon on the Earth or vice versa, you don't add together and compute the interactions of all atoms of one object with all the atoms of the other objects, but you sort of learn that the whole Earth is one mass, the moon is another mass, which is the total mass, and it gives you some approximation of the interaction. When you have the full universe to do this kind of thing, you can do it too. You break it up in clusters. The clusters have to be done at different scales. Again, the mathematics is not the issue here. It's just a scaffold. And by doing this organization, you know that if you have a galaxy here, you have a star here, the whole galaxy is a single object. An interaction of the galaxy with a particular mass or cluster of masses here is given by basically clustering the whole thing. When you get within a galactic diameter from the galaxy, you do something else. You look at the neighboring clusters at different scales and so on. So this, by the way, is very easy to formally organize mathematically so that you don't even have to think about this geometric organization I just described. There is a language to do it. That language is capable, basically it corresponds to what people call multiple algorithms. You can find very special basis expansions to do that. That's fine. But what has happened here is two things beyond the Newtonian mechanics. What has happened is that you suddenly see that the organization, say, in clusters of this universe has actually told you how physical interactions are occurring, and this organization is really a much more precise description of how the gravitational fields are working than the Newtonian description. Again, this is baby stuff. If you were to deal with more complex interactions like the acoustic vibrations in this room, again, you're dead. Classical physics is incapable of doing it. Classical mathematics is incapable of doing it because the interactions occurring here are depending on so many different parameters, and acoustic fields are extremely variable in their property. How are you going to do that kind of stuff? So there is really no language to describe it that we are aware of. So just there is no mathematics. That's what I'm trying to say. There is really no mathematics because people haven't invested, I would say, the time to do it. Let me finish with this sort of brief introduction by just giving you a picture that you may have seen. Where does it? We don't need the screen. Oh, yeah. And you may have seen that could we shut the light for a moment? Yeah. Maybe I should not have described gravitation, but describe this because it'll wake you up. So here you have a picture of the real world. And, but, yeah. Oh boy. There's a clash with the real world. Yeah, unfortunately, it's really not very powerful projector. Well, this threatening animal is a picture of the real world. It's by the way, what I'm telling you here, and we'll may discuss it tomorrow, the analysis I'm going to describe to you of the transcription of this object is one that you need, in fact, in order to compute exactly the acoustical interferences in this room. Okay, so that's not just a picture, it's really a real serious question. And so the question is, how do I describe the geometry of this mandrel? That's really the issue. The geometry of the mandrel and the structures out of which this image is made of. Okay, it's really quite complex. There are lots of mechanisms affecting it, and you would, right, you raise your hand and you say, surrender. So here is a transcription of the object. This is, by the way, the same object, which is described with basically one less 1/3 of 1% the number of parameters. So if the original object has 250,000 parameters to describe it, this one has 1/3 of 1%, and it's a transcription which is done by using this. I'm sorry. I think maybe we'll have a better projector tomorrow. I'll do it tomorrow. It's done by using essentially watercolor. So the transcription here is done by mathematics, completely automatically, using using a. Yeah. Could you try it? Oh, you know, it doesn't. No. Doesn't do anything. Oh yeah, make it. It's done by essentially writing it as a synthesis of various instruments. So here is watercolor. Here is a second layer, which is a Van Gogh type layer. Unfortunately, the colors are sort of washed off in the projector. This is done with a paintbrush, and the last residual is done with a pointillistic fashion by using pencils, so to speak. So what we have is the original image was sort of is a sum of the three, by the way. Is a sum of a synthesis of the image as a sum of three different instruments. One is a pencil, okay, and one is a paintbrush, which is a Van Gogh-like. It does really, the eyes, when you look at it in the right colors, really look like the Van Gogh sun, very nicely so. And the first one is just a watercolor thing. And if our projector was stronger, I would superpose them and show you that the original is the sum of the three stuff. Okay. So it's an orchestration kind of thing. Okay, now again, my point is not, I mean, how it's done and so on, maybe we'll describe tomorrow. That's not the issue. The issue is that somehow there has to be, we start off with the fact that we don't have the language to describe nature. Because we don't have the language to describe nature, we don't have a way of thinking about it. We don't have a way of doing anything about it. Because we are dealing with primitive tools like formulas and modes of thinking that we have been ingrained with. And those primitive tools just, we are dumb because we don't have the words, so to speak. And so the words have to come, and we are not, at least I'm not smart enough to invent them. They have to be sort of discovered in some sense. Discovered by interaction and by fighting with sort of real problem. As Gromov said, for example, how do we describe the geometry that occurs in biology? Well, you can do it, but the problem is it's done by scientists who are amateur mathematicians very often, who don't really care. I mean, amateur in the sense that they really don't care to invest the intellectual effort necessary, the years of work or analysis necessary to understand the actual internal structures of the object. They want to get an answer. So you have various fields like computer science who invent things like neural nets in order to be able to do things like this, or signal processors who do various trickeries in one form or another. Computer scientists of various sorts doing computations, and physicists doing computations, or financial people doing computations, all of them doing it with whatever tool they have at their disposal in an ad hoc, fast way, because they want an answer. And they want an answer, that's great, but we won't get there. There's really, I think it's our profession which should invest the time and effort in understanding the structures and the language necessary to actually do the scientific modeling if we are talking science. That's not the whole real world. And so I think I talked too much already. The main question is what can we as a group do about our field. We are really at a completely pre-Newtonian stage, you know. Before Newton, there was all kinds of hints that calculus is there, various versions of calculus, and so on. And Newton formulated the language needed to describe mechanics very nicely, and then everything sort of opened up. At this point, anytime you have a phenomena with 10 parameters or more sort of interfering with each other, you find out you don't have any tool to describe it. You think you have, but it doesn't work, you can't compute it, and the formulas are not rich enough when you're dealing with pictures which have 250 parameters, 250,000 parameters in them. There's no way. So somehow we need a Newton, which I could say is a new transcription of nature. As a way to proceed forward. Biology is stuck on some level. Chemistry, material science, it's the same problem. I mean, we know the basics, and that's it. Okay, enough said. I would like to actually open the floor really to discussion. I'm sure every one of us has some relation to the real world, so to speak, in terms of his professional life. And the real question is, what can we do? First of all, not to have a canyon between mathematics as it is in the 20th century and as it's going to be in the 21st century. The kids who are coming in are quite a bit more excited by microbiology or by various other fields which look quite virgin territory, where there's a lot to do, and you don't have to be a genius in order to make progress. And it's much harder for us to convince kids that this is a profession that they want to pursue and make a lousy living at. So we have to address this issue. I mean, we have to address it both on the level of telling them that this is a critical profession. It's at the core of everything that happens nowadays. We are really at the golden age of mathematics in a variety of ways, but we manage beautifully to hide it. And how to do the propaganda is a basic issue. Okay, not just for the kids who are coming to study, also for what they will study. I mean, to convince somebody that he needs to have to understand something in algebraic geometry, it's much more effective to show him that he can use it in a variety of situations, and that it's beautiful and relates to a variety of different fields. Okay, whether this or algebra, any one of the classical activities that we are involved with, whether we want to call it classical or not. So the real, I think a good outcome of a meeting like this would be if we got a good set of suggestions on how for us as a profession to interact with the future world. Yes.
Will you open it?
Yeah, yeah. I hear. You just need the microphone. I think we have to start with one.
I have 2 or 3 comments about your really very inspiring introduction. The main theme that I hear from the main theme that I hear from what you say is that you are advocating, let us say, new mathematics for dealing with complexity, or maybe asking the question, how can present mathematics, whether you want to call it classical or modern, but present-day mathematics, how that can be extended, or is it sufficient to deal with complexity? Now, I think that a basic question here is whether there is a unifying generalization. You spoke about Newton. Newton mechanics came in part to explain and to prove, if you wish, Kepler's laws. And he beautifully explained the solar system, which is a system not too complex. If you write the equations and use perturbations and some reasonable approximations, you really get a very good computational description of the solar system, enabling you even to say where it is going to be, let us say, 1,000,000 years from now. Now, the problem that you illustrated about the universe is, of course, much bigger. By the way, has points of contact with other issues such as protein folding, where again you have these clusters of electrostatic attractors that cause proteins to fold, and this is a problem of enormous importance, maybe more important than predicting where the universe will be 2 billion years from now. And people are, as you say, applying ad hoc methods. I think the basic question, one basic question is whether there is a unifying or there are a very small number of unifying principles. So you spoke in a somewhat denigrating form about those people who are doing this and that in order to solve the problems. The question is whether the world is not so complex and the phenomena are fundamentally so different from each other that you would need maybe even a large number of methods. So I think this is a very basic question. The other, and I'm going to describe, not tomorrow, this afternoon, I'm going to describe another, in the discussion of computer science, another extremely complicated situation where classical mathematics is not sufficient. It has to do with the internet, and there you have exactly the same issue arising again. The other comment, the final comment I want to make, is about the picture of the mandrill that you have shown. And that again illustrates the complexities involved. So the question is, how do you parameterize and describe a picture like that concisely, which is in a sense a question of compression dealt with very extensively, again, in computer science and information theory. But then there are other questions relating to, this is computer graphics. So, for example, what computer graphics people do is that they describe an object such as, let's say, an airplane or a person, you. But it's not just to render the front image. They want to have a coding of that image, which will enable also, for example, to rotate it and view it from various sides, and in a sense, if you wish, also look inside and so on, and all that is being done. Say in your picture, there is also the problem, and they solve it, of actually getting the whiskers, say, of the cat or of the mandrill around the mouth. So that's, again, a different issue, and it is solved in another way from the one that you described. Again, an example that the situation is more complex, and that the kind of solution that we like, which is prevalent and catches everything in what we call an elegant way, I would think is probably not available.
I actually meant to really describe an intermediate situation between the multimedia and the mathematics situation. And that is that there is the transcription of the mandrill was designed in order to do computation on it, and not designed in order to look at it. So it's really a very structural situation there. It's not a perceptual situation.
Summarize the comment already?
Yes. The content. Yes, comment. Yes. Just, should I summarize the comment, or you want to summarize it?
Please summarize the comment. It's too complicated for me. I didn't get it. It's like, is there an underlying principle
Yes.
which should be trying to find?
Yes, yes. The comment was, is there an underlying, I would say the essence.
What is your answer?
Oh, the answer is that there are hints of several underlying principles, both in geometry and in analysis, and this is what we intend, Peter and I intend to describe in some sense, that there are universal principles, so to speak, lying in that permit to answer a lot of those questions. I completely agree with you, by the way, that we have to sort of define methods. It seems that the universe has so many different structures that for each one we'll have to invent its own mathematics, so to speak, or find its own internal structures. And that's probably true. The question is, we want to have underlying basic principles that permit us at least to deal with the physical world, say just the mechanical physical world. That's something that we understand much better than the biological one.
Could I add one question?
Sure.
Very short, so that it won't stretch, the absorption capacity of the audience. And the question is roughly the following. Do you think that when we try to describe these natural phenomena, and not only that, also financial world and others,
right,
neural phenomena, there are going to be 3 or 4 underlying frameworks, or are there going to be 20 or 30?
I think we are a little stuck up with with the paradigms of the past. I think that meta frameworks may be very few. Okay, in other words, guides on how to proceed in order to attack a certain class of problems might exist, but then the framework will be very specific to a situation. I don't know. I mean, I wish I knew. I mean, nobody knows as far as.
I don't understand the word which was used. When you say inventing new types of mathematics for dealing with different phenomena, I don't really understand what do you mean by word mathematics.
Yeah, okay. I wish I knew that too.
Generally, as discussion, it is not between him.
Yes, it's between the audience, everybody.
And so when you ask question, ask someone else just to. It is not lecture.
You know,
May I make some kind of remark? So, as mathematicians, when we express our wishes, we also consider possibility that what we want to do is impossible. And so I want to make a statement and usually disprove that first, there is no general framework for describing the world, and there are some arguments in this favor. And secondly, maybe most importantly, as community mathematicians unable to participate meaningfully in that. Yeah? So let me start with the second, which is obvious sociological issue. Because as community, we developed under very particular conditions. Under the Second World War, there was a boom of development in mathematics, and people drawn there were drawn with particular kind of features, yeah, structural mathematics, far from the real world. We build this like that of a community, not chance. We can adjust to the new conditions. There will be different community of different people with different ideology. So there is no way we can meaningfully participate in that. So it's the first statement. And the second is why there is little chance for general theory. First, people tried many times outside physics to do it. Yeah, look, attempts in biology. Mathematicians thought about biology, we feel the structure. All attempts failed absolutely. No chance to realize the structure. And also, if you look how our system, how we have this world is organized, we cannot describe it, but however our nervous system does it. And we have some idea how it does it. It's absolutely perpendicular to how mathematics works. It's kind of broad and very shallow. Yeah? And mathematics cannot be like that. So there are 2 good reasons why your program absolutely has no chance. So can you defend it?
Sure.
What are the 2 reasons?
One, because as a community we are unable to do that because we build, evolve.
We build like this, you mean?
Yeah, evolve for absolutely opposite purpose. And secondly, we have an instant of a system trying to deal with this question, I would say visual system, and also going in the direction opposite to the way mathematics go.
So let me respond to maybe 2 points, which is that many of us have experienced exactly this phenomenon in a great resistance when people try to turn to new kinds of problems and express them in new ways, and your first reaction is to get rejection from your colleagues because they've been trained in a different ideology and they don't recognize even the question. So I'd like to say in response to one of the previous comments that there are certain hints that one sees of smaller numbers of structures than one might guess at. And three examples, which I'm going to talk about tomorrow, very simple examples, are first theory of images, image processing, and second, not specifically Newtonian mechanics in the sense of gravitation, but electrostatics, where in, for example, 3 dimensions, we have very, very little understanding of how an electrostatic potential distributes itself on a surface. If you look at what we know, it's in fact nothing. It's very elementary, and yet the same kinds of structures turn out to be present if you change your view of what an image is. Instead of perhaps viewing an image as an image, view it as a vector lying in some very high dimensional space. And there are ways that look quite promising and fruitful. And another example is exactly financial data, where in the halls of academe there's a great belief that we know a lot, and there are all sorts of fancy courses taught with Brownian motion and Skorohod rules example. And if you look under the hood of this car, you find no motor. On the other hand, we now see a lot of structures that fit into these other kinds of frameworks very well, and there's a lot of hope for understanding them on a deeper level.
I want to make one objection because it lacks historical perspective. Take another instance of this when people are looking at artificial intelligence. And they're also very helpful, and they thought there was a structure. By the way, the approach of Minsky school, in fact, was preceded by the philosopher of the turn of the century. They already tried all that and came to the conclusion it's impossible. So how carefully you analyze possibility or impossibility of this approach. Of course, you are hopeful, you want to do something, you see hints, but you can see much kind of wide historical negative experience showing it's impossible. Yeah? And when you have to face the fact there is no consistent mathematical approach to the problem you consider. And this is quite realistic.
There's not. Yeah, I mean, to me, it sounds like a very defeatist attitude. I mean, after all, before calculus, people thought that the n-body problem is impossible to describe. And I think it took hundreds of years of attempts and so on. But also, I want to make a sort of another point, which would be that we mathematicians, of course, can be allowed to have different points of view. And I don't believe what Misha said, that somehow the social structure of mathematics after the Second World War is such that it cannot accommodate new points of view. I mean, this has happened all the time, in fact. I think you like to talk about history, but I think historically, there have been periods of time when people are interested in certain points of view, and then after 50 years, those points of view are completely abandoned, and people started to look at other things. So again, I don't think we should be so defeatist. Finally, another point I want to make is that in terms of physics, I mean, a lot of us nowadays consider mathematical physics as being whatever has to do with quantum gravity. In other words, with unification and writing down the final equations. There is, however, another point of view, which is that the consequences of equations which are already written are at least as interesting and as important and as difficult as writing down the equations in the first place. And just as an example, I would give Euclidean geometry, where the axioms were written 2,000 years ago, and people are still doing geometry.
Do you want to say something that you want? Yeah, because
I guess I also would like to make a sociological comment rather than a scientific one. I think one of the problems with doing work in an area which is not...
No.
Yes.
You don't.
I have good voice. So I think
Come here. But if you want something to be written on the subject, because microphone is here, record zero. So if you don't want to see this discussion once by someone written, you may, of course, close everything and start. You want to have any input on your own thinking.
Why can't we switch off the loudspeaker?
So you should come here. Is what I'm trying to say. Please, no. Come here. Come here. You will return to your study. But I don't know how to put this in.
By the way, one word only. Now we demonstrate to us, but I will talk later about this a little bit, how good we interact with the real world. We even don't know to use microphone, and we want that real world understood us.
It's a stand-up feedback phenomenon. Well, since Misha started to discuss about sociological aspects of the problems we are discussing, I would like to make a remark on that. I don't believe it's inherent in our community that we cannot innovate or work on something completely new. However, it's a problem of the way we are financed. We are under far too much pressure to produce. So if we have to produce constantly and prove our quality and our performance, then of course we tend to work on relatively risk-free problems, and we do what we can. So I think we should all work into the direction that we are under a little less pressure to publish 20 papers a year. Maybe one further comment. I'm not sure whether it's such a... I'm always a little unhappy if people think that the only challenge is to understand problems that are as complex as possible. I think in the old days, when I was young, the art in science was to find simple phenomena that illustrate basic principles. Nowadays, apparently, people want to do extremely complicated stuff.
Nobody wants to.
Are we forced to? I mean,
Sure. I mean,
things work pretty well. I mean, why?
let's be serious. I mean, if you go to your doctor and he has 10 parameters that he knows about your blood pressure and your age and various other things, and he needs to reach a diagnostic conclusion, he doesn't have any choice. That's exactly the problem.
Hello. I somehow spent a lot of time during the last 2 or 3 years thinking about exactly the things which you were mentioning at the very beginning. And yes, it's real trouble. Things which are happening in mathematics are so far from things which are happening elsewhere in sciences and applications that it is really troubling. However, last year I even took a course in physical chemistry, lab course. I really did the spectroscopy with my own hands and learned quite a bit of quantum mechanics this way. The conclusion which I came to, however, is completely opposite from what you're suggesting. So I think that we should let the kids do the complexity theory and wish them well. We can do nothing about this, and that's my opinion. We're not taught to do this. We have completely different approach to things, and we should do what we know how to do. And if we cannot do this, then we should just all retire. And the best thing we can do in order to make our life better and in order to somehow close this gap between mathematics and natural sciences is to make our mathematics as simple as possible and as more accessible to people on a more applied levels as we can, instead of going down to their level and trying to invent some kind of new mathematics. We have great ideology which developed in the 50s and in the 60s. We've made great progress, and we should make it accessible to the people who can use it.
I think I support very much what you were saying. I think there is a lot of if you look around, almost nothing can be described by classical means. I agree with this statement. And in particular, I think we are all, of course, biased by the way what we learn and what we think is deep mathematics, and we are just blind to other questions which are also mathematical And I mean, even like we had a discussion here about geometry. Now there are at least 2 or 3 other branches of geometry which haven't even come up. Even branches whose very prominent representatives are sitting here and have organized this conference haven't really come up as in the discussion. And that's because we have some of our own views. Now, my own view of the world is discrete, so I could go on now and talk a lot about that. Unfortunately, often a discrete element is missing. So and I'll talk more about this, of course, when I get now. Thanks. Yeah. So, but anyway, what I want to say is that, however, it is not our choice, I feel, to say that what we are doing, and let's do this, because the world is full with terribly exciting questions, very basic questions that like what is the genetic code and how does it work, or how the galaxies arose, or a number of other things, and we just don't know how to describe them. Now I feel that indeed there are some basic principles which maybe are sort of sometimes above the horizon, a little pieces of them, organizing data, which Rafi and I had interesting discussions about. It turned out that some kind of similar ideas arise in analysis and in discrete mathematics about organizing large data sets, large graphs, and so on. Introducing complexities through iteration, and so on. But we understand very little of these, and so I really support that we should try to extend the science in this direction, although it probably will be the job of the next generation.
So I just want to say that let's look at history. I mean, there's this argument that mathematics and the real world are too far apart, and we learn, we can't learn anything about the real world, and we can't teach anything to people about the real world. But if you look at history, look at, say, quantum field theory. I mean, 20 years ago, people probably would have thrown up their hands at quantum field theory and say it's just impossible, and it's given a lot of new mathematics. And also look at dynamical systems. I mean, 30 years ago, I think chaos and turbulence were, well, I mean, I don't know the history of dynamical systems enough, but I know that a lot of it has, a lot of mathematics has come from real world, or some semi-real world study of dynamical systems and vice versa. So, and, 40 years ago, I don't think anybody could predict either of those things. So we look at biology, we look at the many-body problem. Maybe there's really very good mathematics coming from it, and maybe we can tell them something about their real problems. But we're not going to learn unless we try.
Hello. In fact, when I took this, I assumed not to participate in discussion, but do some dramatic step out. But you made sure turn me back. So first, it's perhaps surprising for me how much I agree with all opinion, even though they look sometimes very different. And it's perhaps because we are not one. We will see. Because we are not one-dimensional, and so there is this way to very different opinion to be correct in the same way. Just you emphasize different things. But no one of things which worry people around don't worry me. This is only what I want to say, and turn dramatically to try to another direction discussion. Point is that I believe that problem will be solved by older or younger generation, whatever discussed, just because problem exists. And the fact that this problem of life or just meaning of life will never be solved. Come on. Misha, we didn't describe meaning of life yet, so we are good position. Just because problem which appear and which is obviously should be solved, will be solved. And we will not influence this by saying this one more times. Problem which I want, so everything correct, and perhaps for many people it should be noted. However, what some of organizers thought organizing this discussion was also some different problem of microphone, as I said before shortly. Problem is that we are very far from to be understood by a very small community of mathematicians, and in dramatic time of big wars, great political leader turn to us, and we have again some small time of good life. But when it's going out, it's again misunderstanding between us and real world became huge. So this is a point. Of course, at the moment, there is no problem with people who doing computer science or even a little bit apply mathematics. You know how pure mathematics, or better to say, basic mathematics, because also computer science, perhaps they just did not yet understand that also they will not have students, because to have quickly a couple of $1 million to do some practical software will take also from them all good students. And so this is problem which exists, and it is problem which started in another point. This problem started in the fact that we are not accepted, not by media or politicians, to pay, say, to mathematicians salary which will be competitive with all this terribly quickly developed world. And so this is the point, not salary, but our relation with the world. Not understanding of the world, that the critical point of development of civilization is mathematics. All other things following after mathematics has their breakthroughs, but perhaps with gap of 50 years or more, sometimes less, today is less, and because of this, it's sometimes not noted. And so this is a point, and it is point of us, it is our guild, because mathematicians starting being young, and very in young age usually starting to do great mathematics, have no time to think why they're doing this and what is role of mathematics, why it is important subject. And when you finish to be young, you sometimes much over 60 when you finish to feel this. And so you, again, already started to do history or whatever. So I think this is point of discussion, how we propaganda our importance outside. And this I will try to do this quickly, not to propaganda this to you, but to suggest one of the way which possible to do this, and perhaps it's very naive way, and I don't care, because if naive way may do good job, or even wrong way may do good job outside, that is do. This is not of importance. Now, and so my point of view is that in fact mathematics, its needs, its necessity, is, by the way, I shall only one thing, I also did not think about all these things, but around 10 years ago, which I was around 50, so this was quite already not young age, I was just need to give some talk to Board of Governors on mathematics. And then you had no choice, you had to explain to people who just have money in their pockets and nothing more in, I would not say very dramatically in their brain, but at least not in our direction at all.
That's the brain to make the money.
Yeah, definitely, some part, but not our part. Yes, this is, and this was very, very dramatical experience, because I really worked very hard to say something, and then I discovered that when you work hard, you may understand a couple of points, no matter if wrong. This is again not important in this particular case. So let me tell you what I think about this, and then perhaps some discussion on the subject, how we connect it with this real world. So you see, mathematics, in a sense, exists because our brain is weak. The Lord does not need mathematics. He knows all answers at once. So mathematics is, in a sense, a lever, it depends English or American, yes, of our brain. We increase our muscles, but using one instrument, and we increase strength of our understanding, of our thinking, through mathematics. In fact, I may finish at that point. I just want to explain why it is so. Because if this would be convincing for other people, everyone knows that brain should be used and should be more strong, and then mathematics already would be supported. I don't think that this very simple thought is known And I'm even not sure that mathematicians accept this simple thought, in fact, to understand them. So let me say just a couple of words why it is so. You see, we have very limited ability in our brain, in this piece of meat, as Misha said once. This limited ability is the point that we are able to compare in the same times only 7 different facts. If I have mistaken, it's 6 or 10, it does not change, but it is what psychologists who learn brain said me that it is a number. And by the way, for all people, they said the same. I don't know if it is true. So, because of this, when you need to see consequence, result of some events which depend on more than 7 points, you cannot have this consequence. You cannot see this. Many of us know when you come to your office, because you have more than 7 things to deal, you completely forgot the most important very often. Because whatever left your mind is not under your control. You may keep only 7, something left you. Okay, so if a large theorem of Fermat would be trivial consequence of 8 trivial observation, it would be needs 300 years to develop theory to avoid these difficulties. It would be not seen. For example, but it is trivial and some kind of almost stupid examples. Now, so how we avoid this? Because most things we are doing is this depending on much larger number of parameters, yes? It is unimaginable to think in last century that a huge machine like Jumbo may fly. It is as principal idea would be impossible. Depending on parameters perhaps coming to hundreds, and we cannot observe them, and we cannot believe in this, yes? So, for this there exists mathematics. What doing mathematics? And it is strange consequence, because it's exact not practical mathematics, but the most basic mathematics. We develop theories, absolutely abstract theories. What is abstractization? It is when we connect different things and learn one notion which take into account many different things. So we don't need anymore to think about 5 things. They collapse to 1. Okay? And it is basically a reason why some people don't understand why their colloquial were absolutely ununderstandable. They said very easy things and very easy consequence of couple of, even not many, definitions they put in the start, which people did not know. They did not collapse this definition in one notion. In their thinking, they think about all this developed thing. They accumulate more than 7 points and they don't see consequence. It is triviality. So put 30 minutes on correct explanation of definition, try to collapse this in 1 point, and then you will be able very easy to explain what's going next. So this is in fact very trivial. It is reason why students need much time to learn course, which may be done for 2 weeks, sometimes 3 months. They need time to collapse knowledge to smaller number of points to see consequence. I think in this auditory I don't need to extend this idea too much. I want to say that basic mathematics, basic science, is a critical point in development of civilization, because we built language to be able to talk in small number of pieces about huge number of connections. We built this tree, and it is abstractization. And so when people going to do applied mathematics, so you're going down by this line. Already having these huge consequences, this structure in pure mathematics, we describe back, and back it's easy. Tree going back. You're just going by this, you may go to any direction you later on. But understanding the development of basic mathematics is so crucial, I believe should be extended, should be spent. This is point we should bring to society, to media, to whatever, because if today we cannot solve problem being this ecology or whatever, large system, which everyone talk about this, because pure mathematics did not develop corresponding language, everyone talk about this here. Yes, but this is some kind of right level of language and abstractization we did not come. Money were not put in mathematics, in basic mathematics, not in applied or computer at the moment. So I hope that you have a lot of opinion on what I said and perhaps completely contradictory.
However, just what was said here, yes, I imagined a similar meeting called by fish, yeah, several billion years ago, who wants to remain fish and conquer the land, yeah? You cannot have both. a fish making a meeting 1 billion years ago under the water and saying, we are fish, we have all this power, now it's time to conquer the land, yeah? Yes. But you can't conquer the land, remain fish. You cannot go to the real world and remain a mathematician. That's absurd, yeah? Either you study real problems in the real world, remarkable intellectual challenge, or we remain mathematicians, and there is no...
You answer me, or...
No, just to both of you. We have all these visions, all the beautiful projects, but they contradict the experience we have in the history of humanity, or the history of animal kingdom. You cannot have both, yeah?
I don't understand now.
No, you wish to remain mathematicians, to extend mathematics to apply it to the real world. You wish it. It doesn't mean it's possible. Yeah? Hmm? I'm saying because why fish can fall to the head?
No. Misha. If you answer to Rafi, he will tell you. Just a moment. If you answer to me, it is just sometimes was not so. So I don't want to go to history of mathematics. I just at moment and every moment.
Explain me what Newton was a fish. Newton was a fish.
Yeah, no. Look. It has no relation. Misha, it is your remark going in 10th dimension with respect to what I talk. I agree with this, but it is in...
But I think almost all great mathematicians until maybe 1950s were looking at the real world.
No. It's again...
It takes out, I think, half of what
I talk about different real world. Do they pure mathematics? Just a moment. And mine. Misha, I will answer.
Look, I think we should put this in some...
Yeah, I will say only one small thing. When in time of war, it was first time in time of Viet, a French king was clever enough to understand that to decode the Spanish code, he need mathematician. And from this developed algebra later, but no matter. So, and mathematician had very good life. In time of this war, second war, this code was recovered by Turing or what? Just a moment. And this bring politicians to support mathematics for the next 40 years. They just forgot this already. So this is different thing. You're doing this, what you want to do, what you like to do, but in the same time, having meeting, having discussion, giving interview, which you give sometimes, unfortunately for you, you don't like this, but anyway, it's forced. Yes? You should always remember that you are not ashamed of to be a mathematician. And mathematician is so important key. Not you, but some people. I will give, yeah. I just remember that some mathematicians, Sergey, like, for example, did fund, very much like to do biology and so on. In a sense, many people have this complex of doing pure mathematics.
Very nice discussion indeed. I also like to participate in it, yes. First of all, I would like to make following remarks that 50 years ago, the main tool of our sciences, I mean mathematics, theoretical physics like that, was to understand fundamental laws of nature. And everybody believed that if you will understand them, anything else will be immediately corollary after that. Some people like Fermi will appear after that and will do engineering immediately after that. But I think that approximately after 1980, the understanding, the situation changed. And this is, I don't know whether fundamental law of nature exists or not, but this part of, even of physics became abstract, as I say, more or less like part of pure mathematics. So maybe fundamental law of nature even does not exist, maybe not, but certainly there was a huge crisis in that since early 80s. And so ideology, our ideology are now therefore in state of crisis, that part of ideology, and mathematics became more engineering, and this I believe this engineering mathematics, which certainly had huge achievements, which our chairman told about partly, or at least had in mind, yes, certainly is today, say, #1 achievement in humanity. But I completely do not agree with idea that we should do that and we should not do that. What I heard from my old friends, of theoretical physicists of great generation, they told that they never thought about it. If something is needed, we try to do that. What for? We never told that we should not do that. That's what this kind of opinion itself is some kind of thermometer showing state of decay, intellectual decay of society. This is, and so therefore such things are at least something which I myself don't like, and it does not correspond to the mentality of great scientists of our areas of say 50 years ago. There was no problem for people like Hilbert to combine, say, mathematical logic and mathematical physics and geometry and so on, and analysis. But is this time passed away or not? In my opinion, I was always aware that such beautiful, great science as abstract mathematics, which it is beautiful and great, but for humanity, at least now, for living in humanity where we need to raise money and so on, we need to have some maybe smaller community of leading people which are visibly more clever than others. Otherwise, how to get money? And in that case, I completely agree with our chairman. We have to increase our efforts to make really applied modern area open for best young mathematicians. But this is, there is a huge informational mess in society. For example, algebraic geometry, he starts to do colloquium talk normally. He's absolutely aware that everybody in the room knows what is Matveyev structures or something like that. He does not do this definition. Vitaly told that he starts from brief definition. No, it is wrong. They thought that everybody knows things exactly as in some narrow seminars which we are living in. It is only examples. It's not only this area is like that. Algebraic geometers of more complex area completely stopped, lost ability to write any analytical formulas. They are capable only to speak in some geometrical language. There is also a question in analysis. Almost 99% of people doing applied PDE, as I believe Sergio, and who were trained in mathematics, completely cannot give mathematically exact definition, for example, of such fundamental notions like energy momentum tensor, as I found out. Yeah, I told about that. Okay, let's. You know that, yes. No, you can because you worked with young Mills, but it is. I told not 100, looking at you. Yes, 99 only. Yes. So this is real situation, and somehow we have the. You may think that people have right to do what they can do, but we have to do huge job to open all informational gates for younger people, to make mathematics and applications transparent, to visible for them. And this is what is concerning what we should not do and we should not do. For example, everybody in abstract mathematics certainly thought, at least 20 years ago, that they should not learn and do quantum field theory. Quantum field theory came, started to do best results in abstract mathematics. Almost nobody can learn it, except few number of people, as I told, 1, 2, 3, 4, like that, number of best people, yes, like that. So this is how I understood the idea of our discussion today, I think also idea of our chairman, to make this, our science transparent and unified with its application. in my opinion, there is nothing contradicting in hierarchical structures like with fundamental laws of nature. And people in statistical mechanics introduced, or in dynamical systems, introduced sometimes good understanding of that associated with normalization groups and so on. How to be with these languages and techniques works only partial. In real applications, you have to unify them informally and so on. But I don't see any contradiction between that and old Newtonian or quantum mechanics. It is new development of it, and it is part of our sciences. And mathematics was unique, and was unique with its applications, and it is unique. And it is only, it will be only, say, period of decay of society if we shall forget about that. That's what I have in mind. But it is unique.
I just have want to make two comments. One, so this, as our chairman told us that this kind of interaction of mathematician with other fields kind of going in kind of two ways. That so we just, some people, I don't know, in physics and biology and engineering, they just have problem in some kind of by some their amateurish tools try to apply mathematics, and so which may be kind of sounds bad because they really don't know really great mathematics, so they have to do some simple thing which somehow nevertheless correspond to what they're doing. Or mathematician, some clever mathematician comes into the area and impose their what they know without really much knowledge of what is going on there. And so I think actually it's not too bad when I think it's better when people in some engineering or whatever. It's not only about mathematicians, for instance, like physicists when they go to biology without really understanding what is going on there, it's doing the same thing about brain structure and this kind of stuff. And so I think it's kind of, it's maybe good that we just, these people, by say kind of, without really maybe profound knowledge of some deep mathematics, do this thing, and we just try to understand and then do mathematics after that, not necessarily kind of leading the way. And the second thing is just about this funding problem. So of course, it's the structure of kind of funding of mathematics is really, of course, crucial, and it's really problems. That of course, one thing that there are some established field and established area which kind of got funded, and of course, anything which beyond this, it's, and maybe it's in mathematics, it's not so, but in some fields like maybe closer to computer science, where there is a kind of bigger money involved, and then some groups fighting for the sources of money, and nothing kind of really maybe clever, but beyond this can get into this. But also another problem with funding that sometimes there's too much money going in certain area and it's completely destroyed it. Like, well, in the States we see it with mass education. So really this education in the States is destroyed, in my view, just by the amount of money which put in this education. Okay.
Yeah. There are many topics floating around, and so I'm not reacting to the previous one. You see, we had a century ago, we have some kind of very important attempts took place when Hilbert decided to formalize mathematics. So his assumptions were that it's possible to do, in a sense, one can solve any problem. But by formalizing the question, it was possible to answer it, not in one way in which Hilbert thought, but we have an answer. An answer that not every problem could be solved. We have a paradox. Of course, I don't think anybody understands why so many problems are solvable. We almost can, of course, there are some things like continuum hypothesis, a number of others which we know are independent, but we almost always know now when I see a problem. Could be wrong, but it's clear feeling when problem can be independent we expected to solve. But there was some analysis of the situation done, and then we came to some conclusions. When we're discussing now the relation between mathematics and, say, complex systems, say, real world or something different. So somehow what I don't see, what I would be glad to see, is some attempts to analyze the problem, because whether we say without analysis that we're sure we can solve, or we say without analysis we cannot be sure we can solve, it doesn't have much. And what I see as a problem is to create some way of thinking when we could analyze the problem.
To analyze the problem, whether we can solve.
Whether we can solve, what kind of formulas could we produce? What could be done in principle? The same as Hilbert developed logic to analyze how do we approach to problems. And then we can ask question, what can we cannot be done inside of this framework. I think I would definitely appreciate if I would see some approach to development.
You asked the speaker this question?
Yeah.
What does he say? What ideas do you have if there is some simple answers?
Well, I wish I knew, but there are some things. I mean, there are hints. This is what Peter alluded to before. One thing that is rather clear is that there is a collection of questions which are raised from the sciences, which are basically just the description, sort of the botanical description, if you wish, of the structures which arise in nature, various structures that arise in nature. When you start to look at that, you realize that the basic mathematical principles behind this description, and description should be from the point of view of a mathematician, not from the point of view of multimedia. You want to describe it as an object that you can compute with, manipulate with, do transformation on, and so on. Then you realize that there are very few basic principles. Right. There are more than effective theories. There are two things that happen. For example, the traditional things that has happened in classical mechanics, that you have a moving frame. Now, the objects we are dealing with in the real world is a moving frame in infinite dimension or in a high dimensional space. So the question is, how do you do a moving frame? In that situation, you describe turbulence, and you have something moving around, and turbulence is too complicated for us to describe, so it's not clear whether the problem with handling the turbulence issue stems from our inability to describe the objects that we want to describe, or stems from the inherent complexity of, well, maybe we are really stuck because the language is wrong. We just can't describe it because we don't know how to describe a rough function, for example. And we are going to get very rough functions. It's possible that in a moving frame, this rough function doesn't look that rough. And the whole physics is going to be described by letting...
You mean moving frame, local moving frame?
Local, no, moving frame in function space. Not in 3 dimensions, in functions. Infinite dimension. Well, infinite is 10,000 or a million. That's, I mean, beyond 10, you're infinite. I mean, that's not the point. I mean, from a computational following of this. So we see hints at a variety of different places that such attempts to describe, say, this kind of complex phenomena could lead to some success. I'm not asserting it. I'm just saying there's a lot of hints in a variety of fields that there are unifying principles. We'll hear some tomorrow. Peter is going to talk on some unifying. I'll give some examples. In some sense, the talk Alain Cohn gave, it's sort of the beginning of a unifying principle possible for a variety of descriptive modes. I mean, why is this whole theory developed, right? To describe, say, various complicated foliation you get from an ergodic action. I mean, how... The description, the language to do it, is critical in order to pursue the physics further or whatever the natural thing further. So what I'm saying and what you were saying, in some sense, are very close in spirit. And this will emerge. I think the beautiful thing about what we call applied, actually, the separation between applied and real and non-applied, I think, is completely artificial.
No, but in the example you gave, why should mathematicians try to look for an effective theory in the example you gave of the many masses in the solar system,
Yeah.
why should they look for it? Why should they?
Actually, the
Why should you be optimistic that there's an effective theory
between the different
description and the one that you can deal with?
But the point is there is. There is one.
Why?
What do you mean, why?
Why is there one?
It's an algorithm that describes how to do it in order and computation. And
Oh, you say there is one.
there is one. And there is one for the acoustic. By the way, the acoustic case and the electromagnetic is much harder. I think that he's objecting very. Yeah, no, but he's objecting specifically.
Yeah, it seems to me that in fact there were still huge problems in simulating Newtonian gravity so that you can get reliable results.
The problems lie from the inability of the astronomers very often to be in touch with the computational algorithm.
Okay.
No, but what is the point of your example then? I thought the point of your example was that there are all these problems.
There are problems. This particular problem is a baby problem. The example is just to show this a baby problem, and as just was pointed out, the astronomers are not even using. Okay, they're trying to reinvent the wheel. Okay, it was actually done within mathematics 50 years ago. The translation was not done. The acoustic electromagnetic issue is much more modern, and again, 99% of the community decides to ignore it because it doesn't follow the beaten track, so to speak. So this happens all the time.
Many people who
Yeah, there are many people.
you, 1, 2, 3, 4, but you should do this, not me.
No.
I want to return to the final remarks you made in your introduction. When you spoke about the need to attract young kids to mathematics, you came very close to my area of interest. I might be the only person in this room who in the last few years have been dealing less with mathematics and more with mathematical education. I am currently chairman of the education department at Haifa University in the north of Israel. And I think that if we speak about the real world, if we speak about sociology, if we speak about propaganda, if we speak about making mathematics more transparent, we have to start with education. And the problem with mathematical education nowadays is that it changed so little in the last decades that it's unbelievable. It's true for university mathematics as well, but I'm talking about, let's say, high school mathematics. We teach now exactly the same things that we taught 40 or 50 years ago. The methods, 100. Sorry? 100 years ago. The methods may have changed a little. We now have computerized aided programs to handle various topics in mathematics and so on. But when you think about the content, very little has changed. At the turn of the century, we still don't teach ideas from the beginning of the century, the ideas that came into the forefront with mathematical physics. I mean, a person in Israel can graduate from high school, and I presume it's the same in other countries. You can graduate from high school doing what we call 4 or 5 units in mathematics and not ever hearing the term Hilbert space, and so on. And there are many other examples like this. What I want to say is, I think Vitaly is right in saying that our brains are weak. But we have one thing going for us, and that is we have imagination. And especially kids have imagination. And we have to bring imagination into mathematics at high school. We have to show them, we have to show kids in grades 10, 11, and 12, if not before, how abstract notions in mathematics can be sort of pictorial and can be used in various areas of life. And kids would love it. When you speak about it, they would love it and they would know how to carry it on. And maybe it's the task of mathematicians to think about the curriculum of mathematics in high schools, not just to think about what are the new ideas that should be done in mathematics, what are the new areas that should be pursued in mathematics, but also how mathematics should be handled in high school, because it's really time that we change some of those things. And if I'm already here, I want to make a remark about the discussion we had on Friday concerning Kabbalah and the Bible. Yesterday was Shabbat, Sabbath, and I was sitting in synagogue, and among other things, I was surfing through Psalms. and I came to chapter number 137. And believe it or not, it's one of the most famous of all Psalms. It starts with a verse, "On the rivers of Babylon, there we sat and we cried when we remembered Zion." More importantly, it goes on to also a very well-known verse, "If I forget thee, Jerusalem, may I lose my right hand." Now, this verse is read in Jewish weddings just when the groom, the Chatan, raises his foot to break the glass put in front of him. So I think it goes to show that the important number is not 137, but as it was from the beginning, 1/137.
And I would like to second this statement and what Professor Millman said. And it's not only about the education which has to be taken into account by mathematicians and by the leading ones, I think, because it is very important, but also some kind of public relations should be done also by mathematicians. Who else can do this? I mean, there is a non-existing scientific journalism which concerns mathematics, because the people just don't know the subject, and how can they reflect upon this? And also the popular literature which exists. I mean, since What is Mathematics by Courant and Robbins, there has not been written really much by good people, and then this is, I think, it is not only the students at high school that should have some possibility to approach this, but also people in general, because it is a part of the culture and a part of the society, and it should be spread out somehow. And I think the main mean for this is to be able somehow to give credits for doing this. Even if this is done in a good way, there should be some kind of credit for doing this. But and this is what.
No, I really don't want to talk, but maybe I'm forced. I have a very simple thing to say. And I think I've listened to this discussion and found it very interesting. But for me, the most important thing about mathematics is, it goes back to what Sir Novikov said before, that there are so many wonderful, innovative, interesting, and bright people who do mathematics. And I think that mathematics will survive and flourish if there, in the future, these bright mathematically inclined people who are encouraged to do mathematics. I don't think we can predict exactly what they'll do, but I think if the bright people go off into other areas, then mathematics will decay. And if bright people continue to work in mathematics, we'll have a good future.
Well, I like to express some cautious optimism about the mathematics future, just appealing to my personal experience. When I started my scientific work as a physicist in the Butker Institute of Nuclear Physics, it was in beginning of 60s. I remember very well the background, the typical background of even a bright physicist in mathematics. And that background was relatively poor, and people knew the mathematics of last century. The top of this was the special functions, the theory of Bessel functions like this, or hypergeometric functions was at the top. And during this time, the background of a physicist in mathematics increased enormously. And first, we started the group representation because it was necessary to develop the quantum field theories, and many of topology and such things like inverse scattering and a lot of dynamical systems. So if we look at the problem from the angle, from the viewpoint, how to persuade authority to give money, we can use this argument. so that the role of the amount of mathematics which is involved in applied problem increased enormously in the last decades, and it will increase for sure, because a lot of very important problems. I told about this. There's such simple problem like how to calculate the gradient of pressure in a big tube when the fluid flows through this fluid is unresolved so far, and many other simple questions which are raised in the nature as a challenge for mathematician, and this is a point. And so I think that the mathematics has a big future in application in the sense to in the perspective of application to the real world. But I see two possible obstacles. And one is traditional obstacle. It's a narrowness of people, the very narrow education. And I completely agree with Sergei Novikov that it's very important that people who are bright and have a good mathematical talent, they studied more about the natural sciences to start and build up a bridge from their knowledge to applied knowledge, because sometimes the ignorance of mathematicians is just unbelievable. And I'm in some simple physics, and I faced this problem, this situation, and was really astonished. And another difficulty, another danger, but this is a traditional danger. It's not new. It exists through the whole this century. Another danger is new. It's connected with development of computers, because the capacity of computers, they progress in enormous speed, and they produce a temptation that any problem can be solved just by using a powerful enough computer. And it's not true, of course, because even if the most powerful computer, if the garbage in, garbage out, this is the old story. But the people who do this, they have a big capacity, a good chance to persuade the authority that they are the right people to solve the problem, because they have the most strong computers, and the authority accept such the type of arguments. This is again an experimental fact. And so we should be probably more critical to and there is a lot of scientific journals now which are just a field with a garbage, with a lot of made on computers, and the main thing and a lot of very nice pictures done by the color printer, and but it's very really difficult to understand what's about it and what's the final conclusion of the article, but it's a more or less typical thing. And the real grants are going to these people in much more amount than to pure mathematics. And we should have this in mind. And so I mostly agree. The main conclusion is that mathematicians should be optimistic about their the possible application. I could. There is no time now, but I could show immediately several very nice examples how it could be. But it's a different story. But first, you should be optimistic. Second, the people should try to be as broad as possible in their education, in sense of including the education in physics and other natural science. And the third, the people should be critical to the people who just imitate the science. It is pity, but this is more or less common thing. And I agree that education of young people should be oriented in alignment with these principles. That I finished.
All this talk about practical applications of mathematics makes me feel just a sort of tiny bit uncomfortable, because nothing that I've ever proved has any practical application whatsoever, or I can't even imagine that it ever will have any practical application. So one of the topics that was supposed to be for the discussion was not just applications, but the image of mathematics. And I think it's important not just that we should admit to ourselves that 90% of papers, or possibly more, in pure mathematics are completely useless to, say, engineers or something, like biologists or any but the most theoretical physicists. But also that this is not necessarily a too bad thing, and I think we should think a little bit about just the sheer intellectual excitement of mathematics, independently of its practical applications. I know this is not always an easy thing to justify to people who are giving us money and things, but actually I think it's very important, because it really does cover a large, maybe it's not 90%, but it's a very, very significant proportion of mathematics that we all love, is not to do with practical applications, and we really must convey that this is worth doing as well. And if we concentrate too much on saying, you know, on the practical applications, then there might be some danger that people would say, oh, well, could you please justify your mathematics from a practical point of view, and then maybe try to cut out some of the mathematics that can be justified on other grounds. So that's just the point I make.
I think there is a miscommunication here. Practical applications are just one aspect of a pluralistic society. We are talking about mathematical content.
Yeah, so all I'm saying is I agree with that. So I'm just saying that this is another aspect that we just haven't discussed at all, but it is an important part of the image of mathematics and the presentation of our image to the outside world. That we should be confident that we have some intellectual justification.
Well, so I wanted to say that somehow a lot of the points of view which were discussed could really be made to come together somehow to some unity. So first of all, it's clear that there is a distinction between a physicist and applied mathematician and a mathematician. And as mathematicians, we should really look at problems from the point of view of the mathematical structure involved behind the particular problem. That doesn't mean, of course, that we should not look at problems which come up from the real world. On the contrary. But I think I agree with Misha that not all the problems which come up in the real world can be solved. And certainly we have to, as mathematicians, we have to really come to terms with particular problems in the real world as mathematicians. Like Tim says, that there is a certain excitement from the certain intellectual excitement from the point of view of looking at mathematical structure behind problems. And but this is not necessarily in contradiction with the fact that there are problems, natural problems in physical world, which have a lot of mathematical structure. Certainly, there is no question to my mind that turbulence will be solved, even though it looks like an impossible problem right now, but it will be solved. There is a lot of mathematical structure involved there. And I think it's a very good mathematical challenge for mathematicians. I mean, for people like Tim, who really perceive themselves as mathematicians and not as applied mathematicians or physicists. And I think there are many, many examples like that. I mean, just to give one that I learned sort of a year ago from a chemist. and it has to do with the unfolding, the protein folding problem, which was mentioned before. It's clearly a fundamental problem in chemistry and biology as well, and it seems like at least one of the questions, one of the mathematical questions which comes up there, is something that should really catch the imagination of mathematicians. The question is simply the following. You have sort of a very complicated function in a large number of dimensions, which correspond to the many parameters, many degrees, many parameters involved in the problem. You're talking about the protein. There are obviously lots of parameters. And the question is to find the absolute maximum or minima of that particular function. And it seems to be absolutely fundamental. It's very simple. It's a kind of thing that mathematicians should be interested. And there was, in particular, this chemist was looking for help from mathematicians and couldn't find it, and came up with one way of doing it, which was actually very mathematical, which is the following. You take the heat equation. So you take this configuration for which you want to find the absolute maximum. You run the heat equation. And somehow he claims, of course there is no proof to it, and I don't quite believe, but it's interesting from a sociological point of view. You would run the heat equation, and it will turn, according to him, the only thing that will survive, everything will decay. All the relative minima will decay. The only thing which will survive for a long time is the absolute maxima. And then you sort of go back and you find out exactly what the maximum. I'm sorry?
Simulated annealing.
Simulating in?
Simulated annealing.
Yeah. Wait. I mean, you have to get into a fight with him. I'll give you his name and his address if you want. So it's. I'm sorry.
The question definitely has been considered quite extensively.
Yeah, I know. So I'm just saying that I'm just giving it as an example of a problem which obviously comes up in applications, and it has an interesting, it definitely has interesting mathematical structure behind it, even though Misha will not agree. And I think there are many problems like this. There are all sorts of physical problems which have to do not with finding the equations, but actually seeing the consequences of the equations, which have tremendous mathematical structure, and which can be considered as mathematicians, I mean, we can consider that as mathematicians from our point of view. We don't have to ask the questions that physicists ask. We can ask questions on our own terms. And I think if the questions are sufficiently interesting, they will have consequences in the physical world. That's all.
Because we very quickly should finish, we will give 1 minute, okay, for few people who wanted to say. So come, and Misha and I. Noga, you want to comment also?
Well, I just wanted to regarding the pure mathematicians working with real world application, I wanted to give an example of Van Neumann. So Van Neumann, I think nobody would argue that he is a pure mathematician and a very good one. And I think in introduction to theory of games and economic behavior, he exactly was searching for sort of the right mathematical problem to consider. And he came to a similar conclusion that basically calculus was developed at the same time as analytical mechanics. And in fact, development of analytical mechanics was made possible to some extent only after calculus was invented or discovered. And he also sort of expressed the opinion that the complexity of problems in economics, for instance, is much greater than those in analytical mechanics, so it is to be feared or hope that mathematical discoveries of a statue comparable to that of calculus have to be made. And I think that something like this, I mean, I think that hoping that young people will do it may be over-optimistic, because it is young people who are under pressure to produce 20 papers a year. So I think young people will either produce 20 papers a year in established and well-developed field, or they will go and make money in computer science. I think it's people like well, that's what I...
Well, one remark, that this was discussion.
All right, come.
You'll get your turn.
Well, actually, we don't have time.
Yeah, I think incidentally that's the only person I know that produced 20 papers a year every year is Paul Erdős when he was 80. So keep we keep saying that these young people that have to produce 20 papers a year, but so I think, I mean, the way, yeah, maybe, I don't. So the way I understood Rafi, and I think this was really his intention, but you can tell me if you, is not that all of us should switch now and start to work only on applied problems, right? It's so definitely there is room, and of course most of us would keep doing what we have been doing all the time. And of course there is a lot of place for pure mathematics, but there are also a lot of very nice problems that are connected to real world. So that's the way I understand it. And I think, I mean, to say that outright that we don't even want to consider these problems because there is no hope, then this is good probably to provoke discussion, but I don't think anybody can really mean it very seriously. But you can tell me if I'm wrong here. I mean, that's the way I interpret it. So certainly there is, I mean, we should keep doing what we are doing. We should also probably think about a way of explaining to the public, to non-mathematicians as well, why is it important what we are doing. And you see that sometimes we have, even in this discussion, you see that we often have these problems of understanding what we are saying, right? So there was this, Dennis was asking to summarize the remark of somebody because it's too complicated to comprehend. And imagine what is happening when we are actually trying to explain what we are doing to non-mathematicians. But probably this is also indeed an important ingredient, not only for funding, but for just to keep the subject alive, to attract young people and to somehow keep it interesting. Okay, so.
Yeah, I think time is out for this. For recording purpose. No, just maybe 2 points. I think that one thing that came from my understanding of what Rafi was saying in the beginning, and I think what lots of people mean when they talk about doing mathematics in the real world, is that we are converging to a meaning of understanding a real world problem when we have an efficient algorithm to get the answers to the questions we are asking about it, whatever complex system it is in biology, in physics, and so on. So an efficient algorithm is becoming the definition of and understanding the structure of a complex problem. And I think that's a very important notion, and I think that's very important in mathematics. And in fact, when you start asking yourself, do we understand, you know, a very basic question in mathematics that have nothing to do with the real world, we know that, I don't know, that rational polynomials are a unique factorization domain. Did we understand it? I don't think we understood very much, but now we know that in fact, due to work of Lovaas and others, there is an efficient algorithm to factor polynomials over the integers, and we understand now this problem much more. And in fact, it's much deeper, this understanding that goes beyond that, you know, trivial theorem that we can prove in, you know, to second-year students. So I think this notion of understanding as providing an efficient algorithm is somehow a middle level between having just 1 or 2 or 3 unifying principles and between saying have lots and lots of you know, theories that explain different things. So
yeah, sorry, I cannot just avoid making a comparison. Then in some sense the definition which we're given now is very much in the accordance with definition in the end of 19th century before works of Hilbert. If you look to the so say work of English school on so say computing invariants under group actions, they looked for explicit algorithm, and they refused to accept Hilbert's proof of finiteness of ring of invariance or finiteness of basis of ideal exactly because results, proofs were not effective.
I don't think you understood my point.
No. I just saying that maybe I didn't. It's quite possible. Maybe you clarified. But it sounds as a statement that we try to avoid arguments which we cannot make explicit. And I think the advances of mathematics, starting from the beginning of 20th century, was exactly the realization of possibility to go a long way using arguments which, in principle, so now some of these Hilbert's results can be made explicit. It's very interesting, but the possibility that we can go without making so calculable explicit algorithms was a big interesting discovery. But maybe you clarify.
This is a land of many religions, you know.
We should perhaps end.
Yeah, just a minute. This. Okay. This. Yeah. It's okay. Let's talk about it in the afternoon. But the point. Let me just try and summarize. If anything here came about, it's clear that this is a pluralistic society with different religions, and we don't want to get into religious wars. The main issue really is how do we live together and continue thriving. And the danger at this point is that there is a transitional period in mathematics that is occurring. We really have to come to grips with it. I think this conference can have a major impact provided we do our homework and we each actually give some idea or some input into a definition of ourselves for the future. If we don't do that, it will be viewed as a failure and it will make it even worse in terms of whatever, funding or support or understanding of society.
If nobody wants to say a word for this discussion, there exists next 2 hours, and when we start with this continuation, I have just one small last point because of this right. But I should talk short. Yes. To defend, in a sense, importance of basic mathematics, I would like to say that one of the goals is to discover a new structure, to develop new ideas, new form of thinking, and I believe Tim Gowers is still young enough to see how surprisingly some kind of new infinite-dimensional geometry he discovered will be applied. So, and this is my last point.